And dear students, today I am giving the second video on topology 2. And last class we had discussed about compactness. Today the different types of compactness, and especially we are concentrating on first the sequential compactness. And definition is given: a topological space X2 is sequentially compact provided that every sequence in X has a convergent subsequence. A topological space X2 is sequentially compact provided that every sequence in X has a convergent subsequence. Theorem: every sequentially compact space is countably compact. Countable compactness we had studied last class. So every sequentially compact space is countably compact. That is theorem. Proof: suppose that X2 is sequentially compact. To prove that X2 is countably compact, if possible, assume that X2 is not countably compact. So we are taking a negation argument. Then there exists a countable open cover theta. What is theta? Collection of ui's or I in n, which has no finite subcover. Choose x1 in x, point x1 in x. Then x1 is in u1 for some u1 in theta. We have u1 not equal to capital X because theta has no finite subcover. Okay, this implies there exists x2 in x other than x1. There is x2 in x such that x2 is not in u1. Then there exists u2 in theta such that x2 is in u2. Again, u1 union u2 is not equal to x. Therefore, there exists x3 in x such that x3 is not an element of u1 union u2. Continue like this indefinitely, we get a sequence such that xn is not an element of union ui where I varies from 1 to n minus 1. Now we show that sequence xn has no convergent subsequence. Take an arbitrary element, let x in x be arbitrary. This implies x is in uk for some uk in theta. That is, uk is a neighborhood of small x. We have xj is not an element of uk for all j greater than k. This shows that no subsequence of sequence xn can converge to small x. That is, sequence xn has no convergent subsequence. This implies x2 is not sequentially compact, which is a contradiction to our concept. That is, we have started with it is sequentially compact. Our assumption is wrong in that way, it argues. So x2 is not sequentially compact, which is a contradiction. So our given hypothesis, it is already given, it is sequentially compact, and we are getting that it is not sequentially compact, which is a contradiction. Hence x2 is countably compact. Some results we are discussing. First one, a sequence xn of points x2 is frequently in A, provided that for every I in n there exists j greater than or equal to I such that xj is in A. And this definition already studied x frequently. And we are only recalling the definition. A sequence, second one, a sequence xn cluster at a point small x in x if for every neighborhood capital U of small x, sequence xn is frequently in U. Third, sequence xn clusters in x if there exists x in x such that sequence xn clusters at small x. Only just a variation. Only we are rewriting the second one into third. And fourth one is let x2 be a first countable space, then sequence xn clusters in x if and only if there exists a subsequence of sequence xn that converges in x. Next theorem, every countably compact first countable space is sequentially compact. A very countably compact first countable space is sequentially compact. Proof: let x2 be a countably compact first countable space. Let the sequence xn be a sequence in x to prove that sequence xn has a convergent subsequence. So not, because we have to prove that it is a sequentially compact. That is, every sequence in x has a convergent subsequence. So we are taking sequence xn as a sequence in x to prove that sequence xn has a convergent subsequence. For this, it is sufficient to prove that sequence xn clusters at some point in capital X. There is in the cluster definition. If possible, assume that sequence xn clusters at no point in X. That is the assumption. Let u1, that is union of v in tau, in such a way that xi is not an element of v for all I greater than or equal to 1. Same way, u2 is defined, u2 is union of v in tau such that xi is not in v for all I greater than or equal to 2. Consider like this, in general, you can write a un equal to union of v in tau such that xi not in v for all I greater than or equal to n. This shows that u1 is subset or equal to u2, which is subset or equal to u3, etc. So you take the collection, put theta equal to collection un n in n, which is a collection of countable open sets in x. Now we show that theta covers x. Let small x in x, then sequence xn does not cluster at x, then there exists a neighborhood capital V of small x and I in n such that xj is not in V for all j greater than or equal to I. This implies V is subset or equal to ui. Thus, small x is an element of V which is subset or equal to ui, or small x is in ui. Then theta is a countable open cover of capital X, but x2 is countably compact. Therefore, the x is u1, or instead of that, we are taking the subsequence ui1, ui2, etc., uin. Elements of theta such that capital X is equal to union uij, where j varies from 1 to n. That is, it forms a cover of capital X. Let capital N equal to maximum of I1, I2, etc. in, then ij less than or equal to capital N for j equal to 1 to n. This implies uij is subset or equal to un for j equal to 1 to n, which implies union of uij is subset or equal to un, or capital X is subset or equal to un, which implies xn is not an element of capital X. X suffix capital N is not an element of capital X. Why? Since xn is not an element of un, which is not possible, and hence sequence xn clusters in X, or the theorem follows. Next theorem, let xt be a metric space. If xt is compact, then xt is sequentially compact. Proof: suppose that xt is compact, which implies xt is countably compact. We know that every metric space is first countable. That is, xt is a first countably compact space. So we are using the previous theorem, then it follows that xt is sequentially compact. Next theorem, let xt be a metric space satisfying the Bolzano-Weierstrass property, then xt is compact. Theorem follows directly, or its proof can be done same way. Next theorem, let xt be a metric space, and the following are equivalent. What are they? A, xt is compact. Second, B, xt is sequentially compact. And third, C, xt is countably compact. And fourth one, D, xt has the BWP, or Bolzano-Weierstrass property. That is, we are clubbing together all those results what we have studied earlier to get to this particular theorem. Next theorem is an important theorem. Let xt be a metric space, then xt is compact if and only if xt is complete and totally bounded. This proof. Suppose that xt is compact, then xt is sequentially compact. which implies that every sequence in xt has a convergent subsequence. In particular, every Cauchy sequence in xt has a convergent subsequence, which implies every Cauchy sequence in x is convergent in x, which implies xt is complete. Let epsilon greater than 0 be given, taking theta equal to collection of all such balls BD x epsilon or x in x, then theta is an open cover of x, but xt is compact, therefore the x is x next etc. x in x such that x equal to union I equal to 1 to n of what? These balls, that BD xi epsilon. Let x in x, point x in x, then x is automatically in BD xi epsilon for some I equal to 1 to n. What does it mean? This implies d x xi, that distance is less than epsilon for some I equal to 1 to n, which implies collection x1, x2, etc. xn is an epsilon net for x. But epsilon is arbitrary, which implies xt is totally bounded. Converse case, conversely, suppose that xt is complete and totally bounded. To prove that xt is compact, it is sufficient to prove that xt is sequentially compact. Let a sequence xn be a sequence in x. Since xt is totally bounded, for every epsilon greater than 0, the x is an epsilon net for x. Take epsilon equal to 1, that is you are getting a 1 net. This implies x is a union of finite number of balls with radius 1, which implies that x is a one ball, we call it as b1 such that xn is b1 for infinitely many values of n. Take a1 is equal to collection of such n in n satisfying xn and b1. Clearly a1 is infinite. Now let epsilon equal to half, then we have a half net for x, which implies that x is a half ball b2 such that xn is in b2 for infinitely many values of n in a1. Taking in same way, we are defining a2. a2 is collection of set n in a1 such that xn is in b2. Clearly a2 is infinite and a2 subset are equal to a1. Contained like this, we get a1 contains a2, which contains a3, like that. Choose I1 in A1. Since A2 is infinite, the x is I2 in A2 such that I2 is greater than I1. Find I3 in A3 such that I3 is greater than I2. Proceeding like this, for Ik in AK, find Ik plus 1 in AK plus 1 such that Ik plus 1 greater than or equal to Ik. Now we show that the subsequence xik, where k varies from 1 to infinity, of sequence xn is a Cauchy sequence in x. Let epsilon greater than 0 be given. Find a positive integer capital N such that 2 by n is less than epsilon. Let n greater than or equal to capital N, which implies a n is subset or equal to a capital N, and am is subset or equal to a capital N. Further, in in an and im in am. This implies in, im both elements of a capital N. This implies xin, xim in bn. What is bn? Is equal to bd alpha 1 by n for some alpha in x, which implies d alpha xin is less than 1 by n and d alpha xim is less than 1 by n. Now we are considering d xin xim, which is less than or equal to, you are taking the intermediate value alpha, which is less than or equal to d xin alpha plus d alpha xim, which is less than 1 by capital N plus 1 by capital N, which is equal to 2 by capital N, which is readily less than epsilon. That is d xin xim is less than epsilon for all nm greater than or equal to capital N. This implies sequence xik is a Cauchy sequence in X. But XD is complete. This implies sequence xik is convergent. That is, sequence xn has a convergent subsequence, or XD is sequentially compact. That is a proof of the theorem. Next definition is about the continuous. Uniformly continuous. Let XT and Y row be matrix spaces, and let f from x to y be a function. Then f is uniformly continuous if for each epsilon greater than 0 there exists delta greater than 0 such that if x and y elements of x and dxy less than delta, then a row of fx fy is less than epsilon. Then comes the theorem with the statement let XD be a compact metric space, and let y row be a metric space. Let f from x to y be a continuous function, then f is uniformly continuous. Proof: at epsilon greater than 0 be given, theta is taken as f inverse of b row y epsilon by 2 such that y in capital Y is a collection of open sets in X. We have capital Y equal to union b row y epsilon by 2 for y in capital Y. This implies f inverse y is equal to f inverse of union y in y b row y epsilon by 2, which implies capital X equal to union y in y f inverse b row y epsilon by 2. Hence theta is an open cover of X. This implies XT has the Bolzano-Weierstrass property. Why? Because XT is compact and we are using the previous theorem. Then there exists delta greater than 0 such that for each x in X, BD x delta is subset or equal to some member of theta. That is, BD x delta is subset or equal to f inverse of b row y epsilon by 2 for some y in y. We call it as result 1. Taking two elements x, y and x, we such that dxy less than delta, we have xy elements of BD x delta, which is subset or equal to f inverse of b row y epsilon by 2 for some y in y. That follows from result 1. That is, xy elements of f inverse of b row y epsilon by 2, which implies fx fy elements of b row y epsilon by 2, or a row of fxy is less than epsilon by 2 and a row of fyy is less than epsilon by 2. Now we consider row of fx fy, that is less than or equal to row of fxy plus row of fyy, which is less than epsilon by 2 plus epsilon by 2 is equal to epsilon. That means we are getting the definition of uniform continuity, or this implies f is uniformly continuous.